In this lesson, we're going to learn how to determine enthalpies of chemical reactions using constant pressure and constant volume calorimetry. In any calorimetry experiment, we run our reaction in aqueous solution or in an instrument with known heat transfer properties. If the reaction is an aqueous solution, heat is exchanged between the reactants and the water where they're dissolved. Since we know about how much heat it takes to change the temperature of a gram of water or an aqueous solution by 1 degree Celsius, we can calculate how much heat was exchanged between the reactants and the water by using the mass of the aqueous solution and its temperature change during the reaction. If we're using a calorimeter in an analytical laboratory, we calibrate the instrument before we run an experiment by running a reaction with a known enthalpy and observing the change in the temperature of the instrument. Once we know the heat capacity of the instrument, or how much heat it takes to change its temperature by every degree Celsius, we can run a reaction and calculate its enthalpy from the temperature change that it causes. In both types of experiments, we're measuring the heat, Q, that a reaction exchanges with the calorimeter, and we're dividing Q by the number of moles of a limiting reactant to find the molar enthalpy of the reaction, or delta H. Your first exposure to calorimetry in the laboratory will probably be with constant pressure or coffee cup calorimetry. In coffee cup calorimetry, the reactants are added to the coffee cup in aqueous solution. As the reaction occurs, the reactants exchange heat with the water where they're dissolved, and its temperature changes. Aqueous solutions of the reactants are used because we know the density and heat transfer properties of water, which are about the same for an aqueous solution. The density of an aqueous solution can be assumed to be about 1 gram per milliliter, and its specific heat can be assumed to be about 4.184 joules per gram per degree Celsius. As its units imply, specific heat is the amount of heat in joules it takes to change the temperature of each gram of a material by 1 degree Celsius. We calculate the amount of heat that the reactants exchange with the water, Q, by multiplying the mass of the aqueous solution by the specific heat of water, by the temperature change of the water, which is its final temperature minus its initial temperature. Since the coffee cup isn't well insulated, we also need to account for the heat that was exchanged with the environment before it could change the temperature of the water. To calculate the amount of heat that escaped measurement, multiply the heat capacity of the coffee cup, which is determined before the experiment, by the temperature change. Add the heat that was exchanged with the water to the heat that escaped, and divide the total amount of heat by the number of moles of limiting reactant to find its molar enthalpy of reaction. Let's demonstrate coffee cup calorimetry by performing an experiment. First, we'll need to calibrate the poorly insulated coffee cup to find out how much heat it exchanges with the environment for every degree Celsius temperature change. We'll do this by observing the temperature change in a known amount of water when we place a hotter object with a known specific heat in the water. We heat a 10-gram block of iron by boiling it at 100 degrees Celsius, and we place it in 50 milliliters of water at room temperature, which we measured to be 23 degrees Celsius. The iron exchanges heat with the water, and in the end, they both reach a temperature of 24.55 degrees Celsius. We know exactly how much heat it takes to change the temperature of each material by 1 degree Celsius. Using that specific heat, with the mass and temperature change of each material, we calculate the amount of heat that the iron lost, which is negative by convention, and the amount of heat that the water gained, which is positive by convention. The amount of heat lost by the metal should be the negative of the amount of heat gained by the water if the coffee cup was perfectly insulated so that no heat escaped. There's a difference in magnitude of 15.265 joules between the heat that the iron lost and the heat that the water gained. The difference between the heat lost by the metal and the heat gained by the water must be the heat that escaped. We divide that number by the temperature change of the water to find the heat capacity of the coffee cup, which is 9.85 joules per degree Celsius. The heat capacity of the coffee cup tells us that 9.85 joules of heat will escape for every degree Celsius temperature change, so we'll need to add that amount of heat to the heat exchanged with the water for every degree Celsius temperature change whenever we use that coffee cup in an experiment. Heat capacity is expressed as a positive number by convention, since a material will gain the same amount of heat in a temperature increase as it loses in the same temperature decrease. Now that we have the heat capacity of the coffee cup, we can measure the enthalpy of a chemical reaction. Let's measure the enthalpy of the reaction of magnesium with hydrochloric acid. We put 0.25 grams of magnesium in a coffee cup that already contains 50 milliliters of an aqueous solution that contains enough hydrochloric acid to consume all of the magnesium. The aqueous solution in the coffee cup rose in temperature from 24.25 degrees Celsius to 45.77 degrees Celsius. Let's calculate the enthalpy of the reaction. First, we calculate how much heat the reaction exchanged with the water to increase its temperature. We can assume that we have 50.25 grams of water, since we have 50 milliliters of aqueous solution and 0.25 grams of magnesium in the aqueous solution after the reaction. We multiply the mass of the solution by the specific heat of water by the temperature change of the aqueous solution to get the heat exchanged with the water. Now we adjust for the heat that was lost by the poorly insulated coffee cup. We take the temperature change of the aqueous solution and multiply it by the heat capacity of the coffee cup that we previously calculated. This gives us a total of 4,736 joules that were either transferred to the water or lost to the environment. Now we're going to find how many moles of magnesium we used by dividing the mass that we placed in the cup by the molar mass of magnesium. We divide the total amount of heat by the number of moles of magnesium, and then we make it negative because the heat that was released by the reaction is opposite the heat that was transferred to the water or lost to the environment. The experimentally determined enthalpy of the reaction between magnesium and hydrochloric acid is negative 460 kilojoules per mole. In a modern analytical laboratory, you might be using constant volume calorimetry to measure enthalpy of combustion. In constant volume calorimetry, the sample is placed in a metal cup in a chamber that's pressurized with pure oxygen gas to make sure combustion is complete. The chamber is placed in an insulated container full of water. When the button is pressed, electrodes heat a filament in contact with the sample, and it causes the sample to ignite. The burning sample transfers heat through the walls of the combustion chamber into the water container, which is stirred continuously to distribute the heat from combustion. The temperature of the calorimeter is monitored with a thermometer so that its temperature change can be recorded. To find the amount of heat transferred to the calorimeter, the temperature change in degrees Celsius is multiplied by the heat capacity of the calorimeter, or the amount of energy that it takes to change the temperature of the instrument by each degree Celsius. The heat capacity of the calorimeter is measured before the experiment by calibrating the entire instrument with a sample that has a known enthalpy of combustion. To calculate the enthalpy of combustion of the sample, divide the amount of heat transferred to the calorimeter by the number of moles of sample. The heat gained by the calorimeter is a positive number by convention, so the heat released by combustion of the sample should be a negative number, making the enthalpy of combustion negative. Let's demonstrate constant volume calorimetry by performing an experiment. First, we'll need to calibrate our calorimeter by finding how many kilojoules of energy it takes to raise its temperature by each degree Celsius. We'll use a sample that has a known enthalpy of combustion to do this. A small tablet of benzoic acid is often used to calibrate a constant volume calorimeter. We weigh our tablet of benzoic acid. It weighs 1.025 grams. Benzoic acid has a molecular weight of 122.12 grams per mole, so we have 0.008393 moles of benzoic acid. Benzoic acid has a known enthalpy of combustion of negative 3228 kilojoules per mole. We multiply that by our number of moles to find that our sample will release negative 27.09 kilojoules of energy as it burns. So the calorimeter is gaining positive 27.09 kilojoules of energy. We burn our sample in the calorimeter, and the temperature of our calorimeter rises from 21.50 degrees Celsius to 23.40 degrees Celsius. To calculate the heat capacity of our calorimeter, or the amount of energy it takes to raise its temperature by each degree Celsius, we divide the amount of energy gained by the calorimeter by the temperature change that it caused. Our calorimeter has a heat capacity of 14.26 kilojoules per degree Celsius. Again, heat capacity is always a positive number by convention. Now that we've calibrated our calorimeter, let's burn a sample of stearic acid to find its enthalpy of combustion. We load 0.357 grams of stearic acid into the cup. Stearic acid has a molecular weight of 284.48 grams per mole, so we have 0.00125 moles of stearic acid ready to burn. We place the cup in the chamber, set the electrodes, pressurize the chamber, put it in the water, and press the ignition button. As the sample burns, the temperature of the calorimeter rises from 23.20 degrees Celsius to 24.17 degrees Celsius. We already calibrated the calorimeter, so we know how much energy it takes to raise its temperature by each degree Celsius. Multiply the temperature change by the heat capacity of the calorimeter to find how much energy was gained by the calorimeter. Our calorimeter has gained positive 13.83 kilojoules of energy, so our sample has released negative 13.83 kilojoules of energy. To find the enthalpy of combustion of the sample, divide the energy released by the sample by the number of moles of sample. We have determined that the enthalpy of combustion of stearic acid is negative 11,000 kilojoules per mole.